Okay, we're going to finish up this chapter here. Like I said, we just really have just kind of ethers left to talk about. We're going to talk about ethers and a couple of properties, obviously a couple more of the properties of alcohols. And then we will talk about a couple of reactions that aldehydes and ketones undergo with alcohols that I talked about with the other class, half of the class there the other day. So just make sure everybody's on the same page. All right. So ethers is really the next sort of functional group that we're going to talk about here. And the functional group of ethers is, again, a carbon oxygen to carbon sort of run. Ethers always has that oxygen between two carbons here. And because of that, they oftentimes will have this sort of bent shape, because basically the guy in the middle is pretty much like water. It has the 4 electron pairs and 2 bonds, which gives it that kind of bent or V-shaped sort of geometry. Now, there's a couple different ways to name ethers. We will go with the common name here, and I will tell you or show you the other way of naming it, which is the more formal way of naming it. But maybe your book, I think, maybe sticks with the common name, so we'll stick with that. So it's pretty simple when you go to name sort of an ether. You pretty much just find the oxygen, and then you pretty much look to the right and to the left, and you find basically the groups that are there, and we kind of name them as groups. So to the right there, that's a 1 carbon group, which is a methyl group. To the left is also a 1 carbon group, which is a methyl group. And since that's 2 methyl groups together, we basically just use dimethyl and just put ether at the end. If we had something like this, in this case, we would look at the oxygen in the middle, and we would go to the left, and that is a methyl group. To the right, there is a 2 carbon group, which would be an ethyl group. And we do put the groups in alphabetical order. So this would be ethyl, methyl, and then we simply just kind of put ether at the end of it. So the common way of naming ethers is pretty straightforward. Like I said, the best thing to do is put a box around that oxygen, look to the right, look to the left, and just kind of see what is attached there. The sort of more IUPAC way of naming, which we will not go with here, but just in case it comes up somewhere, it's a little bit different. We actually take the longest carbon chain that's attached to the oxygen, which in this case would be 2 carbons, and that would be ethane. And then the shorter carbon chain that's attached to the oxygen, we drop the YL part of it and put oxy on it, and this is what is referred to as methoxyethane. Oxy there for the shorter carbon group, and then ethane for the longer carbon group. So that's the more sort of formal way of naming it. In this case, we will go with, again, the common way of naming, but just in case that other way pops up, that is sort of how you do it. Longest carbon chain, just name it like a normal alkane. The shorter carbon chain, kind of gets the oxy part of it at the end of the name. Any questions on that there? So here, if we do our common name, we would focus here on the oxygen. And again, to the right, there's a 3 carbon group, which is a propyl group. To the left is a 1 carbon group, which is a methyl group. Again, in alphabetical order, this would be our methyl, as we see there, propyl. And again, just put ether at the end of it. If we were going to take the more IUPAC way of naming, again, just to show you how that works. Once again, the longer group here is really propane. Shorter group here is methane. And we drop the last part and put oxy on it, and that makes it methoxy. Propane would be, again, the IUPAC way of naming. Probably much easier going just the kind of common name in terms of our ethers. Ethers, although they do have an oxygen, will have sort of not as strong boiling points and melting points because they cannot necessarily hydrogen bond with themselves. They might be able to do a little bit of participation with some water, but it's not going to be very strong sort of bond with themselves as they cannot hydrogen bond. So obviously ethers are used to, you know, put you to sleep during certain times. When you're having maybe some type of surgery. Over the years, they've replaced ethers or a lot of things on ethers with a lot of fluorine groups. Gives it a little bit more easier to work with, not as flammable as well, which is, I imagine, good since they're giving you that probably to go to sleep during the surgery, so you'd have some issues. All right, so let's try a couple of these. Why don't you draw? We'll do the one that's there, diethyl ether. Why don't you draw ethyl, actually butyl ethyl ether. And why don't you give the name for this guy here? Okay, let's take a look. So we're drawing ethers here. Best thing to do is really just start with the oxygen, especially in this case where we have sort of the common name. So diethyl ether means that we have an ethyl group on either side of the oxygen, and ethyl is a 2-carbon group. So we would just fill in our 2 carbons with the appropriate number of hydrogens there. Any question on that one there? Same thing here. We're going to start with the oxygen, and now we have a butyl group, which is based off of butane, which should be 4 carbons. And again, it doesn't really matter which side you draw it on, so I'm just going to do it on the right there. We also have an ethyl group, which is 2 carbons. And once again, we're just going to fill in our hydrogens here to get each of those carbons to the 4 bonds. And then we should be good in that case, yeah? Any questions on that there? Naming, we will focus in on the oxygen, which tells us it's an ether, as we got a carbon, oxygen, carbon. To the left here, I got 1, 2, 3, 4, 5 carbons, so that's a pentyl group. And I have a 1 carbon over here, which is a methyl group. And putting those together in alphabetical order, it's going to be methyl, pentyl, ether in this case, yeah. Or was referred to as methoxypentane if you use the IUPAC way of naming. Any questions on ethers, how to draw them, name them? You do need to be able to obviously know the functional group. You do need to be able to name them as well, yeah, and draw them obviously. Yeah. Any questions on that? I'm sorry, what would the name be? The last one that we did? It should be methyl, pentyl, ether, alphabetical order. Yeah. So other questions? Yeah. All right, so we talked a little bit about some of these properties of alcohols. Again, how to classify them. Once again, the easiest way to look at the carbon that has the OH group attached and how many carbons are attached there. So that's 1. This guy obviously has 2 as secondary, and this guy has 3 carbons attached to it, which makes it obviously a tertiary alcohol. As we talked about with those reactions, it's important as to what you get. Again, if you oxidize that primary, we get the aldehyde. Oxidize it one more time, you get a carboxylic acid. Oxidize a secondary, we get our ketone. And again, you will not oxidize a tertiary because it is missing the hydrogen on the carbon. Now, in terms of solubility in water, alcohols definitely are soluble in water because, again, as I mentioned earlier, they could do that hydrogen bonding, which makes them very soluble in water, as they have that OH group, and that R is just a carbon type group. Negative and positive, when it interacts with water, they are both using the exact same intermolecular force that they use with themselves. So they use hydrogen bonding with themselves, so they're able to hydrogen bond with water. Makes it very, very soluble in there as well through hydrogen bonding. As I mentioned before, though, as the number of carbons does increase, and again, usually about 5-ish or more, you really do start to see the solubility start to decrease with water. And that is because you just really have a non-polar part that's too big for water to interact well with it. So if you have something that has a ton of carbons, I won't draw all the hydrogens, but pretend there's hydrogens. And then you just have this OH group at the end. This part here, which is nonpolar, is really too big, gets in the way of water interacting with that OH group, and it definitely decreases the solubility of it. Remember as well, in order for something to be soluble in water, it has to replace basically water and water interactions with very similar interactions. Water is a relatively small molecule, so trying to put something that's really big in there doesn't really work very well, even though it may have that OH group. We also talked about earlier today as well, if something has more than one OH group, that definitely does increase the solubility in water, and that is typically what we will see. And as I mentioned before, as you can see, 4 or less, you know, you're not too bad in terms of the alcohol, but at that 5-ish point or more carbons, pretty much not going to be soluble. Ethers as well will be relatively soluble in water a little bit because it's able to interact well with water through the oxygen. It cannot hydrogen bond to itself, but it can participate a little bit with water, so it'll be a little bit soluble. Phenols will be slightly soluble in water. They run into a little problem because they got this big bulky benzene ring kind of hanging off of there. So it gets it a little bit in the way. So they're only slightly soluble in water. They can react with water in more of an acid-base reaction where it will kind of donate the H plus over, kind of like an acid. And the water here would act more like a base, and you'll make this sort of negatively charged guy that's left over along with our positively charged guy here. That OH group can form hydrogen bonding with water, but again, that kind of bulky benzene ring doesn't make it perfectly soluble in water, so it has a little bit of issues with it. Let's talk about another really important point in terms of these type of interactions, which is things like boiling points and melting points, and specifically boiling points. So when we talk about some of these groups that we've been talking about, you know, we have alkanes and just basically hydrocarbons, which are just carbon and carbons. We have things like our ethers. We have things like our aldehydes and ketones. And we have things like our alcohols here, right? So in terms of boiling point and even melting point, really these things are affected by how strong these potential molecules can sort of interact with themselves. So if you remember, sort of, there's really 3 types of intermolecular forces. There is hydrogen bonding, which is a bond between hydrogen and nitrogen, oxygen, or fluorine. So the hydrogen needs to be directly bound to a nitrogen, oxygen, or fluorine for it to hydrogen bond. This is what polar molecules use. When they have that bond, like water that has the OH bond, it's able to do hydrogen bonding. There is dipole-dipole interaction, which is how polar molecules interact with each other. They basically interact with the positive side of one, attracted to the negative side of another. And because these are polar molecules, they always have a positive side and a negative side because of their dipole moment, the unequal sharing of electrons as a whole. So they're good to go. And that's pretty strong as well. The weakest of all interactions is dispersion forces. And these are really temporary type forces. They are also sort of a positive negative attraction. The difference though is these occur very temporary. They need something to occur for it to happen. Normally, these are nonpolar molecules which do these things. And normally nonpolar molecules pretty much don't have a charge because they have equal sharing of electrons over the entire thing. And that basically means they have no way to interact with each other. All ways that molecules interact with each other is pretty much the same way. Positive, negative of one are attracted to each other. So when you have a nonpolar molecule that's just by itself, it doesn't have a positive side, doesn't have a negative side, so it has no real good way to maintain interaction with other sort of molecules as well. But what can happen in a nonpolar molecule is the electrons could just decide to go to one side or the other, and that will temporarily create like a positive side and negative side, and that temporarily gives them a way to interact with each other. So these things will temporarily gain sort of charges, and that will give them a way to interact with each other. But what happens is those electrons will go back the other way, and then they'll break apart and new ones will form, and then those electrons will go away. And so it's kind of a constant, like, we have attraction, we don't have attraction, we have attraction, we don't have attraction, kind of like your cell signal. You got like 3 bars, then you got 2 bars, you got 3 bars, right? So it kind of goes fluctuates back and forth. As opposed to dipole, when you have polar molecules, which no matter what you do to those things, they always have the positive and negative side. So they're always ready, good to go. They're able to interact with each other. So in terms of strength, this is really the strongest type of interaction, and this is the weakest. Now, because alkanes and just basic hydrocarbons are pretty much carbons and hydrogens and nonpolar, they pretty much will use dispersion forces pretty much as their main route of interaction, which means they aren't held together very tightly because of that. And that's why a lot of those things like methane, propane, butane, they're gases, right? Because they're not held together very tightly, which means they could go into the gas phase really, really easily. Something like an alcohol, which has this OH group, can participate in hydrogen bonding with itself, which means it's going to take a lot more energy to break it apart and get it into the gas phase, which means it will have a higher boiling point than something like an alkane. So things that can participate in hydrogen bonding typically will have a much higher boiling point than somebody that cannot. And it varies. We do have this carbonyl group, as we talked about, which is kind of polar, right? It's got a carbon oxygen side. That is this side more negative, this side more positive. So in terms of boiling point, kind of like how I wrote it here, boiling point and all that increases in terms of these functional groups as you kind of go that way. Alcohols is the strongest in terms of boiling points. They'll have the highest. Alkanes will have the weakest, and our aldehydes and ketones and ethers are kind of in the middle of those guys in terms of their boiling points and melting points. Any questions on any of that there? Yeah.
So you're saying that the alkenes have lower boiling points, and then it just kind of goes from alkene, ether, aldehydes, ketones, alcohol.
Yeah, alcohol at this point is pretty much the highest boiling point you could get because it has that ability to hydrogen bond with itself. We will see something in the next chapter, which is carboxylic acids. They actually can beat alcohols. They're one of the few things that will actually have a higher boiling point than an alcohol. But pretty much your alcohol is usually your pretty highest boiling point. Then you'll have your kind of your ketones and aldehydes below that, your ethers, and then on the very opposite end where you have your lowest boiling points and melting points are really just like your hydrocarbons, like your alkanes and those guys. They're basically just carbons and hydrogens. They're nonpolar. They're not going to be held together really tightly, which means it doesn't take a lot to convince them to go into the gas phase, which is why when you work with organic chemicals, a lot of times they put you in a fume hood because they're not held together very tightly. So just very simply, they'll just go into the gas phase. They're sometimes referred to as being volatile, which is a lot of cases not good because they are sometimes flammable. So that's why we kind of stick them a lot of times in the fume hood. Any questions on that there? Yeah. That pretty much wraps up this chapter, except that I did want to talk about 2 reactions that aldehydes and ketones undergo with alcohols, and then we'll all be caught up here, I think. So we'll start with our aldehyde and our ketone here, and we're going to react it with an alcohol. So again, we're going to be looking at this functional group or this functional group, reacting with basically this functional group. So we'll start with the aldehyde. So we'll just take a very simple aldehyde here. Looks something like this. And we're going to react it with a pretty simple alcohol as well. We'll just do this guy here, alcohol. So when this occurs, when we take an aldehyde and react it with an alcohol, as we talked about previously, pretty much everything's going to occur right here. at that carbon oxygen double bond. It's pretty much where all is going to happen. And as we talked about, the oxygen part of that's more negative. The carbon part is really more positive. And we're going to do sort of like an addition reaction here. And we're going to add this alcohol in kind of two parts. This oxygen carbon part is going to be added, and then this hydrogen part is going to be added. And you could also think of the alcohol when it adds like that as having charges as well. The hydrogen will be more of a positive charge. This oxygen carbon will be more of a negative charge. So what's going to ultimately happen is we're going to put those guys on kind of like what we do with H2, Br2, HO2, H2O, HBr. We're going to put one part of it over here and one part over here, but we cannot do it with the double bond still there. So we do have to get rid of the double bond. So that's what I'm going to first draw. It's just this whole thing, removing the double bond, because that's going to allow room for these guys to come in. And what's going to happen here when we add one alcohol to an aldehyde is opposites attract. So the hydrogen will be attracted to the oxygen, and this negative oxygen carbon group will go down to the carbon over here. And that is going to put a hydrogen over here. And that is going to put that oxygen carbon group that comes from the alcohol over here. And what we just made actually has a special name. It is what is known as a hemiacetal. You could think of hemi because it contains OH, and acetal because it comes from an aldehyde, basically. Right? So it kind of comes from an aldehyde, and it has that OH group. What makes something a hemiacetal is if you look at a carbon, it will have these components. It will have an OH group attached. It will have some type of oxygen carbon group that comes from the alcohol, like this guy here. And it will also have a hydrogen. So those are the three kind of main components for something to be basically a hemiacetal. Now, if you just add one alcohol to that aldehyde, that is what you're going to end up with. If you add two alcohols to that aldehyde, you will end up with the hemiacetal. And then that hemiacetal will continue to react. So if I just start with what I just made there. And we add one more alcohol to it. And I'll do the same alcohol. It doesn't necessarily have to be the same alcohol, but I'll throw the same one up there. And in this case, it's still going to add very similarly to this, except a couple of things are going to be a little bit different. And the thing that's going to be different is if we look at our alcohol, we're still going to add it the same way as sort of this. And that's still going to be kind of a positive and negative. The difference is here, we're going to make water. So in order to make water, we're going to steal the OH that we made from the hemiacetal and the H there from the alcohol. And those two guys are going to make basically water. And that will give us our H2O, which is our water. Now, what that leaves is our hemiacetal exactly the way it looks without the OH on it. And the problem with this is our carbon is short a bond, right? So it doesn't have enough bonds. We have already used this hydrogen, and we've obviously already removed that OH. So really the only thing left at this point is that oxygen carbon group. And that is what's going to go to the carbon that needs the bond, because really the carbon that needs the bond is actually still relatively positive. So that oxygen carbon group that's left over, which is this guy here, is still negative, and really this guy is still positive. So it's going to end up right there where the opening is. And now we basically added two parts of the alcohol to our aldehyde. And this has a special name, which is known as an acetal. And that is what you get when you add two alcohols basically to an aldehyde. You basically end up putting on there the alcohol minus the hydrogen in each case, the oxygen gets connected in. What makes something an acetal is if you look at the carbon will have two oxygen carbon groups attached. So oxygen and carbon, and it will still have the hydrogen because it comes from an aldehyde. So those three parts is what makes something an acetal. So the addition of one alcohol to an aldehyde makes a hemiacetal, which should have an OH group, an oxygen carbon group, and a hydrogen. Adding two alcohols will actually transfer two oxygen carbon groups to your aldehyde, and you'll still have that hydrogen there. Question on that one there. Now, the ketone actually does pretty much the identical reaction. You just get slightly different sort of outcome because a ketone is slightly different looking than an aldehyde to start with. So let's see what would happen if we did this exact same thing with our ketone. So if we started with a ketone, and we'll just do a nice simple ketone here as well. So we have our ketone, and we'll add an alcohol to it. Again, we'll do a little different alcohol in this case. So the same thing is going to happen as it did with our aldehyde. We're going to focus in on our carbon-oxygen double bond. So it's all about here. And once again, this is going to be more positive. This guy's going to be more negative. And our H is going to be added. And our oxygen carbon group here will be added. So once again, just like before, we need to make room for those guys to come in. So we'll do a CH3, a carbon. We're going to make our double bond into a single bond, and we'll do our CH3. Now that we've made room, we're going to get really the same addition that's going to occur. The hydrogen is going to be attracted to that more negative oxygen. This oxygen carbon group will go find the carbon that is there. And the result of that is we will make our OH, and we'll get our oxygen carbon group attached here, which is this there. This also has a special name. This is what is sometimes referred to as a hemiketal because it comes from a ketone. So that's a hemiketal. Hemi again because it has an OH group. What makes it a hemiketal is that carbon, which is this guy right here, has an OH group attached. It has a oxygen carbon group attached, but it does not have a hydrogen. So no hydrogen like it does in the aldehyde, because the aldehyde has a hydrogen. It does not have a hydrogen. I will say that some books will still call this a hemiacetal, even though it's kind of a hemiketal. So some books will just group them both the same, basically. So you may see it called a hemiacetal as opposed to a hemiketal. But it's basically derived from a ketone where you add one alcohol to it. And just like what we did with the aldehyde, if we were to add two alcohols to it, it would continue to react. So what would happen is our hemiketal would continue on, and we would add the second alcohol to it. And again, I'll use a smaller alcohol in this case. Why not? We'll just do that guy. And once again, we're going to make water in the second step here. And again, that's going to be negative, positive. So our water, once again, will remove that and the hydrogen there from our alcohol. And we will get our water that is formed. The hemiketal here will pretty much stay intact, except that it loses the OH. So everything else stays the same. Nothing changes. And just like the last time, we've already got rid of these two. We've already used this big thing. So this is the only thing that is left. And that is what gets added on here. And this has also a name that is referred to as a ketal, again, because it comes from a ketone. And it has the same sort of groups. It has two oxygen carbon groups that come from alcohols attached to it. And once again, no hydrogen. Again, some books will still call that an acetal as well, but a lot of books will call it a ketal as well. So if you take a ketone, add one alcohol to it, you make a hemiketal, which has that OH group and the oxygen carbon. If you add two alcohols, it takes it all the way to the ketal group there. Any questions on that there? All right, so I just want to go over that reactions with you. I would again recommend, as I mentioned before, when you're drawing these products, don't overlook what's in the question, because again, a lot of times you do have kind of pretty much the answer in front of you. You just got to change the one part of it. And again, it's really just pretty much in most cases where the functional group is really the part that changes. Nothing else changes. Everything stays the same. So if you ever find yourself not sure what to draw, just copy what's there to start with, and you have probably most of it, but obviously you need to change some things. Any questions on any of this stuff here? All right, are there questions or anything I can help anybody with? So Le Chatelier's principle. It has to do with really a certain type of reaction, which is what are referred to as reversible reactions. And these are the reactions where you see the arrows headed in both directions. And basically, that means that there is a forward direction that goes from reactants to products. But at some point, what happens is the products will recombine and make the reverse reaction occur and make some reactants. So it's basically a reaction that will go in both directions. And what happens in this situation is it eventually will reach what is referred to as equilibrium. And sometimes people think equilibrium means that you have the same amount of reactants and products, on both sides of the arrow. And that's really not what it means. What it's referring to is really the rate of the forward direction will equal the rate of the reverse direction. And what that essentially means is when something reaches equilibrium, it will just as quickly go to products, and those products will just as quickly go to reactants. And what that does is it essentially will lock everybody into place as to where they're at that point. So when it reaches equilibrium, whatever concentration everybody is, they will basically be able to maintain those concentrations because it's going back and forth at the same rate. We can visually look at it and go, nothing's happening. But if you were like super zoom in, there's a lot of activity. Everybody's going back and forth at the same rate. And that's what maintains basically everybody's concentration the same. So the idea of Le Chatelier's principle is this: you have a reaction that's at equilibrium, and then you do something to it that frankly screws it up and is no longer going back and forth at the same rate. So you have this system that's at equilibrium, and you add what is sometimes referred to as a stress to the system. And a stress can be concentration. It could be pressure or volume. It could be temperature, or it could be a catalyst that you do. And basically what happens is you do something to the system that's going back and forth at the same rate, and you screw it up. But the system itself wants to get back to that state of going back and forth at the exact same rate and reach equilibrium again. So the way that it tries to get back to equilibrium is it will do one of two things. It will shift to the right, which means it will make more products. It will shift to the left, which means it will make more reactants, or there will be no change, which is a possible option that could occur. So let's talk about what happens when we do concentration, for example. If we have concentration, there's basically two things you could do. You could either add more or you could remove. And when we add more, it will always shift away from the side we added it to. And if we remove, it will shift towards the side we removed. So, for example, if we took a nice teeter-totter here and we put some stick figures on there, and this is our reactant side, this is our product side. And let's say that somebody hopped on the product side. So we put more products in there, right? What's going to happen is this got teeter-totter is going to kind of do this deal here, right? This guy's going to go up and maybe not be so happy about that. Yes. So in this particular case, to fix this, do I need to put more people on the left or more people on the right? I do need to put more people on the left. So it's going to shift away from where I added. And we need to put more people there on the left-hand side. And what's going to happen is it's going to once again come back to equilibrium. And everybody will be happy in this particular case. Now, if we have the same system that was at equilibrium to begin with again here, we're starting at equilibrium. And again, this side's our reactant, this side's our product. And let's say the guy on the right decides to hop off. So like we remove some products, right? We took some stuff out. The result of that is this is going to happen. Not so good. To fix this, we need to put more people on the left, more people on the right. We do need to put more people on the right. So it's going to shift to the right, to the side of where we removed it from. And once again, it will be able to come back to equilibrium at that point. So the reason why it shifts away when you add something is basically you're making that reaction occur. So if you add more reactants, there's a lot more reactants. They will start reacting and make products. If you add more products, that's going to cause the reverse reaction to occur, and they will make more reactants. When you remove something, which you could do by making a precipitate, you could also make water as a way you can remove something. You could think of it as making a hole on one side of the reaction or the other. So if you remove products, there's like a big hole on the product side, which means you have more reactants. So they're going to start to react to fill the hole back up, right? And that's why it's going to go towards the side you removed it from. And if you remove some reactants, it's like a big hole on the reactant side. You'll have a lot more products. They'll start reacting, and the reverse reaction will occur to kind of fill back up basically the reactant side there. So if we had a reaction, say like this, and I added more B and I removed C, which way would it shift in each of these cases? If I added more B, it should shift to the B is on the reactant side, and when we add, it should shift away. AA is a good way to remember that. It's going to shift that way. If I remove C, C is a product. It's going to make a hole over here on the product side, which means it needs to fill that hole. So it should also shift to the right to fill that hole. Yeah. Question on that there. Yeah. Now you could also have something like pressure and volume. And these are usually occur with gases. And we talked about gases and our friend Boyle, right? There is a relationship. It's not spelled right. Boyle, try it that way. Boyle's law, which says that as the pressure goes up, the volume goes down. And as the pressure goes down, the volume goes up. So there's that opposite relationship. So in a system that's in equilibrium that are gases, so for example, let's say we had this, and these are all gases. If I increase the pressure, that means that the volume is going to get much, much smaller, right? So the change that's occurring is the pressure is increasing. We want to bring the pressure back down, but the volume now is really, really small. The way to bring the volume, the pressure back down is, do I need more gas molecules in a small area or less gas molecules? What would happen if I put more gas molecules in a small area? The pressure would continue to go up, right? Too many gas molecules in a really small place, more collisions. So if I put less gas molecules in a small volume, that should bring the pressure back down, right? Opposite of that is basically it will then shift to the side with the least number of gas molecules. And that depends on the equation you're looking at. You basically can count the coefficients and see how many each side has. If you do the opposite, pressure goes down, volume goes up. It will shift to the side with the most gas molecules. And that's because basically what happens is the pressure starts to drop in this bigger volume. So in order to bring the pressure back up in a bigger volume, you need more gas molecules. So pressure and volume, a good way to remember it is by the volume. Small volume, less gas molecules. Bigger volume, more gas molecules. So for example, here, if we increase the pressure of this mixture, that means that the volume should go down and I need less gas molecules. On the left-hand side here, just counting the coefficients for anything with a G next to it, there are 3 gas molecules on that side. This side has 4. So in this particular case, which way should it shift? The one with the smaller number of gas molecules is this way, yeah? So it should go to the left, yeah? So pressure and volume are always sort of tied together, and I personally think volume is the best way to think about it. If you remember Boyle's law, pressure goes up, volume goes down. So small volume, less gas molecules. Pressure goes down, volume goes up. Bigger volume, more gas molecules. And again, you just got to count the coefficients for anybody that has G's in front of them. Question on that there. The last type of sort of change that could occur in Le Chatelier's principle involves temperature. And it works the same as concentration, which means that if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards. And it has to do with whether or not the reaction is exothermic or endothermic. And if you remember, exothermic means heat and energy is released, and heat and energy is absorbed in an endothermic process. Exothermic things also have a delta H values that are sometimes given as positive values for endothermic, and there should be negative values here for exothermic. I said the right thing, put it in the wrong spot. Let me put it there, which is negative. But when we look at a reaction that is exothermic, we think of heat and energy as a product. And when we think of an endothermic reaction, heat and energy is a reactant, is thought of. So if we were to increase the temperature of an exothermic reaction, that would be like adding more heat and energy to the product side. So it should shift away, and it would shift to the left in this case. If we removed heat and energy from an exothermic reaction, that would be like creating a hole over here on our product side, and it would shift towards the product side. For an endothermic, it would be opposite. If you increase the temperature of an endothermic reaction, it's like adding more reactants, which will cause it to shift to the product side. And if you decrease the temperature of an endothermic reaction, it would be like making a hole over here on the reactant side. It would actually shift towards the reactant side. So temperature really works the same as concentration. You just have to determine is it exothermic or endothermic. And there's a couple different ways that you could do that. They might write heat in the reaction on one side or the other. They may actually put a number on one side or the other, or they may just give you the delta H value, which is known as the enthalpy. And it doesn't really matter what the number is, it's really the sign that's important. If it's a negative value for energy, it's an exothermic process. If it's a positive value for energy, it's an endothermic process. The last thing that you could do in these situations is add a catalyst or something like a noble gas. And either one of these things will basically cause no change to occur. Noble gases are chemically inert, so they don't react with things. Catalysts will just make the reaction occur faster, but won't make a shift either way. The other way that you could get a no change is like the gas example that we were just talking about. When you count up the number of moles of gases, they're the same on each side. So that's like a push. So there'll be no change that would occur. So if you did something where you change the pressure, but there's like 4 gases on the left and 4 on the right, it's going to cause no change because there is no side that's more or less in that case. There's your 5-minute Le Chatelier's principle.